I'm Tanya, and I'm the project manager of Purdue's space program High Altitude. High Altitude is Purdue University's only two-stage rocket team. Our long-term goal is to launch a two-stage solid rocket to the Kármán line. Our team is excited to be competing in the Argonia Cup for the second time with our new rocket, Barracuda. Our team consists of roughly 80 team members spread across 6 sub-teams: structures, mechanisms, propulsion, avionics, simulations, and business. We're extremely excited to share more about our rocket with you today, so let's get into it.
High Altitude operates on a yearly design cycle, which means we devote our fall semester to designing and spring semester to building and launching our rocket. During the fall, we start with onboarding and then move on to our preliminary design review and then our critical design review, where we finalize the design of our rocket. During our onboarding process, new members design, build, and launch their very own rocket within 8 weeks. High Altitude places significant importance on the transfer of knowledge as well as technical and professional development.
Hi, I'm Venus. I'm one of the project engineers. In order to prepare for the competition, we have designed a 3-flight test campaign to test various functionalities of our rocket before the full-scale launches at the Argonia Cup. The goal of our first test launch is to test our second-stage ignition capabilities and our recovery system. The goals of the second and the third launches are to test the structural integrity of the rocket with more powerful subscale motors. We bring all of our team members out to test launches to give everyone hands-on experience with integration, test, and launch operations.
Our simulation sub-team designed the rocket using MATLAB, ROS Aero, and Open Rocket optimization algorithms. We designed our rocket to be minimum diameter to increase aerodynamic efficiency and decrease weight. We determined that a payload of 13 golf balls would maximize our score for our current design and motor configuration.
Hello, my name is Srinikesh Kalandur, and I'm the structures co-lead. The rocket is a total of 120 inches in length, with the stages being in a 40-60 ratio and the sustainer being in 60 inches. The rocket is minimum diameter, with the inner diameter being approximately 2.15 inches. During the rocket design phase, one of the main objectives was to minimize the height, as that helps reduce drag, but also increases overall structural stability and integrity. Each stage has 3 fins, with the booster fin having a root chord of 6 inches and the sustainer fin having a root chord of 5 inches. Each fin is attached with sanded fillets made of a 2-part epoxy adhesive as our primary structural bond. Measurements for the fins were calculated and tested with simulations to ensure that we obtain optimal stability while also having maximum altitude for the competition.
Hi, my name is Mia and I'm one of the structures leads. As part of the competition, we will be compressing 13 golf balls in between the sustainer motor and the AV bay with some styrofoam discs to reduce vibrations. To reduce the overall weight and length of the rocket, both of our motors in the sustainer and the booster will be retained using friction fit. Due to our motor selection this year, we are no longer able to use our traditional motor as coupler interstage, so we have the flare. The flare is an internal to external coupler that will slide into the booster and go over the sustainer motor. There is an internal ledge on the sustainer that will allow for thrust transfer and also let the nozzles of some of our motors stick through the coupler. On the booster side, there is an internal bulk plate to act as a hard point for our chutes of the booster and allow for pressurization for separation.
Hi, I'm Adriana. I'm the Avionics co-lead. So the Avionics team is responsible for flight data acquisition and analysis, telemetry, ignition, and lockout timing. Our student research and developed computer that accomplishes this is called PAL 9000. So every year we continuously update the PAL 9000 firmware to be more robust and more capable. So new changes that we've implemented this year are the extended Kalman filter, which helps to improve state estimation and reduce sensor noise. Additionally, we have implemented an atmosphere model to better account for changes in air density, pressure, etc. At different altitudes. We also utilize a commercial off-the-shelf computer. The one we'll be using this year is called the Blue Raven. And it's important to have 2 separate flight computers for redundancy and safety to ensure that all systems function as planned.
Hi, I'm Kevin, the mechanisms lead. My subteam's role is to make sure that the rocket is recovered in a reflammable condition, and so one of the constraints of the competition states that the maximum descent velocity of the rocket should be 35 feet per second, and so we use a descent velocity formula to calculate our sizes for the parachutes, and then we double check that with the descent velocity calculator given in the Fruity Shoots website. Speaking of, we have in our booster stage a 30-inch main parachute, and our sustainer stage an 18-inch drogue and a 30-inch main parachute. We pack these parachutes in an optimized Z-fold so that it fits tightly and nicely inside our airframe, and we pack these parachutes inside Nomex blankets in a burrito fold so that it does not sustain any potential damage from black powder charges. We also have cable cutters on our sustainer main parachute, which I will talk about in a little bit. We also connect everything through 1/8 inch Kevlar shock cord. We used computer-aided design to 3D print our avionics bay with the use of PETG filament, which has a strong structural integrity to keep our flight computers safe. We also have a mechanism that connects our avionics bay with the bulk plate, which is then fixed inside the airframe. All of our chargers are connected to the avionics bay to have a controlled ignition. So when the booster stage finally reaches its max altitude, the black powder charges will ignite, separating both stages and also deploying the main booster parachute to safely recover that stage. Then, when the sustainer reaches its max altitude, the black powder tube charges will ignite, separating the nose cone with the airframe, which is still connected to the airframe through the shock cord, which then deploys our drogue parachute. And we have our main parachute still held together with cable cutters so that it does not prematurely deploy, making the rocket drift away. So at a certain altitude, then the cable cutters will cut the zip ties so that our main parachute can finally deploy and safely recover our sustainer.
Hi, I'm Alexa. I'm the propulsion lead. So for the booster motor, we'll be using a K1275 Aerotech motor with a standard Aerotech igniter. With that igniter, we won't be inserting it until we clear the launch pad. And for the sustainer motor, we'll be using an Aerotech K270, and we'll be using a quick-dipped E-match to ignite that motor. We have a 100% success rate using E-matches for igniting our motors.
Thank you for taking the time to learn more about our rocket. Our team learned a tremendous amount about designing and building two-stage rockets, and we're so excited to launch amongst all the other incredibly talented teams out at the Argonia Cup in a couple of weeks. Boiler up!